design team. I am Tristan Deetsky.
Anastasia Winslow.
Matthew Beckham.
Quandre Grady.
And our client for this project was Lieutenant Matt Fan of the U.S. Coast Guard. He is with us right now. And he gave us an issue that he wanted to solve with his training program, which is that many people in the U.S. Coast Guard did not fully understand how ungrounded systems and the shore power connected together could cause issues. So our model is all about implementing situations that show how you can have problems when you put shore power in incorrect configurations.
So the goal of our model was to build a realistic version of the ship-to-shore power connections that shows two different scenarios. We wanted the user to be able to interact with the model so that they could create their own ground faults safely and then see the current in the wire that happens from them. We broke the model into 4 different modules, where each one of us was in charge of a different module.
I was in charge of the power module, which was responsible of taking a power from a 120 volt AC outlet, so your standard wall outlet, and converting into 3-phase power to be used by the rest of the system. This is replicating the power systems on board U.S. Coast Guard cutters and other naval ships.
I was in charge of the dock module. I took the 3-phase power from the power module and sent it through transformers, which created 2 isolated circuits. One of the circuits had 2 parallel connections for the boats, and the other one had the ability to be grounded for our 2 different scenarios.
My module was the BOST module, so it essentially took the three-phase 120 volt AC outputs from the dock module, and using the system of the relays and the ground fault detection lights, as well as the copper tubes that were placed in the water, using signals coming from the MCU, it would create the ground faults as well as activate the ground fault detection system, and that value that was read, and the value of the current in the water would be read in the display module later on.
And I was in charge of the display module. I was just in charge of taking the analog signal switch, converting it to a DC signal that goes to the relays that are on the boat and shore power modules, and also taking that information from the current readings and sending it to an analog emitter.
Okay, so this is our project architecture. This is a previous mock-up of our design. So you'll see it takes power from the Walt 120 volt AC, steps it up, going to the VFD. The VFD creates a 3-phase signal, sends that to the 3 transformers, which gets the 3 outputs of 3-phase 120 volt AC. And those feed into the boat module. Those have the system of relays that switch both the ground fault detection lights as well as the copper tubes right here. And that's all controlled by the display, the MCU. Our current model does not have the screen. We'll go over that later. But it's switched by actual manual switches. But that controls the circuitry of the relays and everything. These are some current photos of what our project actually turned out to be. So this is the VFD right here. We actually blew one of them up previously. That's our.
For those not don't know what a VFD is a variable frequency drive. It pretty much uses pulse modulation to convert a single-phase AC signal into a 3-phase AC signal. So this is the inline ammeter that we chose to use instead of the actual clamp-on ammeter that was going to be connected to the screen. Those are the system of breakers that are used for safety. You can see the transformers up there, the step down, and then the 3 that broken down into the 3 outputs.
And then this is the actual boat module right here. It's hard to see inside of there with the circuitry, but there's one of the relays. There's a delta circuit that connects to the lights and creates the demonstration.
Over the course of the project, we've come across several different modifications for the various modules. For the boat module, the first one we came across was we're using plastic boats instead of metal, like they actually use in the Coast Guard for safety reasons. Because of that, we have a copper tube that touches the water that a user cannot touch for safety. We also are using a acrylic tank for aesthetic purposes. We actually repurchased several different things for aesthetic purposes, since we have a client who's going to be using this a lot. We're also using an analog ammeter instead of a clamp-on ammeter. For the dock module, there are dual wound primary windings. We're using both of them in parallel. Our original design only used one of them. We needed the extra current to go through the water. Display module, we ended up using a completely different MCU and not a screen. We used analog. We used manual switches instead and the analog ammeter to display the current. And for the power supply, we added a buzzer for safety reasons. And the power supply is not directly powering the MCU as we initially thought it would.
So this is kind of like a breakdown of how our schematic is set up, just giving a clear description of how we get power from the wall outlet through the power supply, and that goes into the dock module. This gets split off into two isolated circuits, one for shore power A, one for shore power B, and then those power the boats as well as the control system that we have. The display module has 3 analog switches that then control all the relays for all the different components in the buzzer and the power supply, the ground and the dock, and then the ground faults in boat 1 and 2.
Okay, now running through the scenarios that we covered. So this one right here is through a ground connected transformer and a ground fault on the boat itself. So the ground fault is triggered, the ground fault detection light goes out, and the grounded transformer, there's a path for the current to travel through. It completes the circuit, and that could potentially harm any divers in the water. Scenario B is between 2 boats that both have a ground fault. What's important to note here is that they're both connected to the same isolation transformer, which allows this error to happen. What's also important to note is that these 2 ground faults are on 2 different phases. If they were on the same phase, no current would be traveling through the water. And this is the neutral scenario, how it's supposed to be oriented. 2 separate isolation transformers for each boat. And you'll see that even though these both have a ground fault that's actually being detected on the boats and is occurring, there's no current traveling through the water because they are on 2 separate isolation transformers.
And then this is the main flowchart that was implemented in my code. Overall, it checks the system, whether the analog switch was flipped or not, and if it wasn't, it'll stay. If it is flipped, it'll get reset back to 0.
So deliverables and milestones. So we started off back in September. We met with our client and we proposed the initial idea for the in-ground power model. We went on to the proof of concept in November. And we had a VFD malfunction, needed to buy a new one, so we did not end up doing that one. The display did not work for it, but we did get to measure current in the water for that proof of concept. This year we started building the modules, and we had 3 of our 4 demos succeeded. The display module was not working still. So then we went on to start integrating the modules. And we had eventually on April 9th, we had a successful demo of everything after we switched the MCU to a new one. Everything worked. And then for Excellence Day, we won Best Veteran Poster. Coming up, we're going to hand off the model to our client, and then we'll do our final report.
And then for the budget, like all the other design teams, we got a $1,000 budget. Overall, we used $945 of that budget. For actual materials used, we only used about $645 of that budget. And then extra material that we had either in the lab or Mr. Knapp gave us. That was about $305 of that. And then for our team wages, it was based off of the averages in South Carolina for electrical and computer engineers.
So our current status is we have completed our demo 4 and have a fully functioning project. We have been making it more aesthetic as we go along, which as we see in the model upstairs, looks real nice right now. The delays we've had have been mainly with demo 3 and demo 4 where we had to rework the display system and its controller. We've had to make revisions in the code. We added in a analog meter rather than the digital display, as well as switched to analog switches. And those were most of our delays. Okay. Review of the project summary. Currently with everything we've been given or had to buy, ended up being around $940 out of our budget.
So a quick summary of the achievements, right? We produced a functioning product that worked well and demonstrated the dangerous situations that can occur when things are not done properly. We gained experience integrating all the modules into one working product, and we learned how the design of the product significantly differs in application and all the experience you need to actually get this thing to work.
And for future work, we plan on implementing a clamp-on ammeter to work with the display module, which I did not get to work in the beginning. Any questions?
So, you know that some submarines have DC shore power. Say the Navy wanted to get a hold of this, I don't know if any surface ships use DC shore power, but how would that be implemented into something like this, since it's arguably more dangerous than AC shore power?
So for DC shore power, you have to keep in mind that a lot of the way DC functions is you definitely need to have a complete circuit for DC, and in cases like this, I don't know how that would fundamentally change because a lot of it depends on where it's able to ground and what sort of path the current has to flow. And most DC systems, just like high voltage wires, you can touch one wire and not have a problem as long as you're not grounded. Because you need to be able to return back to the source. AC, on the other hand, since it is going back and forth, you can have potential problems because you get other problems like capacitive coupling and inductive coupling, which can create paths for current flow.
Two more questions. So one is for the design of the final model, did y'all have any constraints on that you were using?
So our client requested that the model be a small size so that he could make it easier to transport. That was one of our initial ones. He also requested that we use a wall outlet to plug it into.
And then the tank itself, for making the water like conductive, were y'all using like cylinder like the ocean, or is there just
We're using tap water. The pier for the U.S. Coast Guard base is actually on one of the rivers, so it is fresh water. If this wasn't salt water, it probably wouldn't be as much of an issue in the current in the water. It's less effective.
Did y'all have any problems, like unexpected issues, like trying to seal it down so small? Did everything's kind of go because about expected?
Yes, we had quite a few problems managing the voltages and currents necessary. My first test of the power supply, I actually blew up these, not realizing that oscilloscopes are naturally grounded, so I was creating a short through it. Other than that, we've had to do adjusting, how do I say, to get an actual readable current through the water, we had to bump up the current in our transformers and dock modules by putting the dual wound transformers in parallel on the primary side to draw more current. And I also had to install a filter on the end of the VFC signal so that we got a more stable waveform out so that we could read the current.
How, if any, do industry standards influence what impact the project?
So we had to extensively look at the NEC, NFPA standards and NESC, as well as the IEEE standards to conform with the ways we did insulation. We had to look up if breakers were required and what ratings of those breakers, which is why we put in quite a few additional safety features. Part of the reason why we have a buzzer on the power supply system is because it is required for ground fault detection systems. If you purposely initiate or have ground faults, you have a audible and invisible warning. Let's see. I believe that covers most of the standards we had to conform to and work around.
Ease of maintenance, is it easily, is there like a drain plug on the bottom to easily drain the water out? And is it easily reproducible so they can be used at multiple Coast Guard locations?
The tank is not attached to the base. We have it so that you can completely take it off and drain it and make sure it's dry before putting it all in. And it, I also made, so there are supposed to be like permanent wires going to the boats for the relays in there. We made them so you can disconnect, so the whole thing can be like, the whole tank part can be taken off for transportation purposes. And then for reproducing, most of the parts are very easy to come by. We are going to give our client a very comprehensive schematic and how to go through the scenarios and all the list of parts that he can do his own maintenance and potentially reproduce it if you want.
Based on your experience in this project, what do you recommend to the Coast Guard? Do you recommend grounded power? Do you recommend ungrounded power? Is there any takeaway for me to learn from you?
So from my experience with the Navy and knowing what's required of these vessels, ungrounded power is more reliable, just because these are ships meant to go into dangerous situations where damage can occur, and using grounded systems, if you have a common ground throughout a ship, it can lead to causing more damage just because of now you have a path for current to go. Ungrounded systems, even though it may, cannot fully, explained well in most places, having one fault won't cause too much of an issue if you correct it. It's, you get into the problem when you have multiple faults that can be able to connect the power and complete the circuits that causes damage.
Thank you.